Well, numbers are not going up, so maybe we should start, right? Welcome everyone to our last day of our workshop. Today will be devoted to gravitational wave detectors. Our first talk will be given by Tanya Regimbau, and it's going to be about the search for a stochastic gravitational wave background in LIGO, Virgo, and K-graph. And I think without further ado, I ask Tanya to please share her screen.
Yeah, sure.
Then you'll have 35 minutes.
Okay.
I'll let you know when you have only 5 minutes left. Okay.
All right.
And please, everyone, go as the talk goes. Please pose your questions in the chat, and then in the end of it, we have 5 minutes for questions.
Does it work?
Yes. Yes.
Okay. Just put the.
Everything seems fine. Please go ahead.
Okay, thank you. So I'm going to talk about the search for a gravitational wave stochastic background in LIGO, Virgo, and K-graph. The background, this stochastic background, is a very interesting tool to study physics beyond standard models. There are other ways, of course. Some have been discussed already, like primordial black holes in LIGO, and I will not discuss that today. I will concentrate on the stochastic background. For some reason, okay. So the stochastic background is the result of the superposition of a large number of independent and unresolved sources. We distinguish between a cosmological background that, can you see when I show on the screen? I hope. So there is a
yes, we can. Sorry.
That's nice. There is a contribution that is the signature of the very early universe, so close to the Big Bang, time of inflation. And on the top of that, there is an astrophysical background that was created much after, since the beginning of stellar activity. So here, so when galaxy and black holes and neutron stars have been formed. So when we speak about the stochastic background, first way to define it, to think about it, is a family dinner, for example, or a cocktail party. So if you are in a room and there is a family dinner in another room, or if you are arriving to a cocktail party, you can see that many people are discussing, but you cannot distinguish individual voices. You can just hear some big noise. And another way to think of it, which I prefer because I study it as a source that is full of information, is to think about a concert. So in an orchestra, you have different instruments playing together, some melody, some symphony. And the same if you are in the audience, unless you have a perfect ear, you cannot identify individual instruments. Okay, so I'm realizing now that with the COVID, maybe in a few years we will explain the family dinner and all these things with the stochastic background. So first, a few words about the cosmological background. So I guess it has been discussed a lot during this conference. It's often seen as the grail of gravitational astronomy. It's a unique window on the very early stages of the universe, much before the CMB, and on the physical law that apply at the highest energy scales, higher than what you can have at CERN. And the first background we were thinking about when people started to think about these things is the one from inflation, that is the result of the amplification of vacuum metric fluctuations during inflation. And for this background, you don't need sources, but on the top of this one, you can have active sources that could have enhanced the gravitational wave production at the end of inflation. So there are nice papers from the LISA collaboration, for example, where they define and discuss that pretty well. So you can have particle production, reheating, spectator fields, and also the primordial black holes. And there are other models that have been covered a lot during this conference, which are cosmic phase transitions, and also the topological defect like cosmic strings or superstrings. So how do we characterize the stochastic background? By analogy with the CMB, we assume that this background is Gaussian, stationary, isotropic, and polarized. Gaussian means that you have so many sources arriving at your detector at the same time that even if the distribution of the gravitational wave amplitude of one source is not Gaussian, if you add them together, it will always result in a Gaussian distribution. And if you have these assumptions, you can define the background, you can characterize the background by what we call the energy density parameter. It's given by the energy density in gravitational wave per logarithmic frequency, interval of logarithmic frequency, and it's normalized by the rho c, which is the energy density to clothe the universe today. So here I'm just showing there are spectra here, cosmological spectra from inflation. In blue, you have okay, I have problem with my mouse. In blue, you have what we call the slower inflation model. And it's there is a constraint given by the CMB. And in addition, so it's quite low, and also it's decreasing with the frequency. But in some exotic model of inflation, you can have extra contribution at higher frequencies. So here are just some examples, and the parameters are set so that they can be seen, for example, in by advanced LIGO, Virgo, and Cagra detectors. So it's not written Cagra because it's an old figure. So for example, you can have action inflation coupling or stiff equation of state. So there are many models that can be quite optimistic. For LISA, if you change the parameters, you can have the contribution in LISA or LIGO, Virgo, Cagra. So something that is not directly related to physics beyond the standard model, but which is really important for us because it can mask this cosmological background we want to detect, is the astrophysical contribution. It's expected that this contribution will be higher, the one from the cosmological background in the LIGO, Virgo, Cagra frequency band. And this astrophysical background is formed by all the sources that we cannot detect individually. So at the moment, we are detecting binary black holes, binary neutron star, and since recently, black hole neutron stars. So these ones are quite close, but there are many more sources at high redshifts that we cannot see individually, and together they create a stochastic background. This background is interesting because it is complementary to individual detection. So we would be happy to detect it first. It can carry a lot of information about the star formation history, the evolution of the metallicity, and also about the mass distribution, their evolution with redshift, the spin distribution. But as I said, it can also mask the cosmological background. So in the end, we will want to remove it. One thing that can distinguish the cosmological background from the astrophysical background, and I will go back to that after, is the properties in the time domain. It may not be continuous, meaning that we may not have a source present at each time, or it can be non-Gaussian and even non-isotropic because of the distribution of the galaxies. So I'm going to discuss first a bit the background from these sources we are detecting at the moment, because we detect already binary black holes, binary neutron stars. We are able to constrain, to have an idea of the background from all the sources we cannot detect in the universe. So as I said, the events we are detecting now are the loudest and the closest events, so that their amplitude is high enough so that it is above the noise. Well, not above the noise, but we can extract them from the noise. And there are many more at large distances. This background includes, of course, the contribution from primordial black holes. We are not able to say whether it's a primordial black hole or a stellar black hole, and certainly at the moment it would be difficult to, if we had a detection of the background from compact binary, it would be difficult to separate the contribution from stellar and primordial black holes. I'm not really going to discuss this contribution. I can refer to the nice talk we had yesterday. So this background from compact binaries is the one that is expected to dominate in the frequency range of LIGO, Virgo, Cagra. And it has to be removed so that we can study all the other cosmological background and then physics beyond standard model. And using the mass distributions and also the rates we can derive from the first observations, we were able to predict what amplitude and what shape this gravitational background could look like. So the background from any type of astrophysical sources, and here binary neutron star or binary black holes. We'll not talk about neutron star black hole because we have not done, at least we have not published the calculation at the moment. The article about the first two detection of black hole neutron star is quite recent. But it should not change a lot because this contribution is low compared to the other two. So omega, the energy density, can be expressed as the flux, which is F. And this flux is just the sum over all the sources in the universe. So there is this integration over redshift of, so the rate, so the number of sources per interval of redshift, and a quantity, DEDF divided by 4 pi and the luminosity distance square, which is related to the spectral properties of individual sources at that redshift. And this is called the fluence. And here, for simplicity, I have used the average mass, but you can also integrate over all the parameters like spin and masses. So the calculation we have made in the LIGO and Virgo paper assume that these sources are essentially from stellar origin. So the rate is derived from the star formation rate. So DRDZ is the rate per interval of redshift. It is obtained by multiplying the rate per interval per volume divided by 1 plus z to correct for the redshift and multiply by the volume. And to calculate this rate for the stellar binary black holes or binary neutron star, we use the star formation rate. And we have also to include the delay, the time delay between the formation of the massive stars that are going to become black holes or neutron stars and the time to the merger. If it were binary primordial black hole, we will not use the star formation rate like that. It will be another rate. So that's one difference between the two models. And also, of course, the mass distribution and the spins. So the calculation here I've made for stellar mass black holes. This is the energy density, the expression of the energy density in the unspiral phase and assuming circular orbit, which is fine in the LIGO-Virgo-Kagra band. And we stop at the last stable orbit for binary neutron stars, but for binary black hole, we also include post-Newtonian correction for the inspiral phase, and we add the merger and the ring-down phase. So this is an analytical expression that can be found in a paper by Ajit, 2011. So doing that, this is what we obtain for omega. And if you compare with other predictions for cosmic strings or phase transition, you can see that it's expected to be a bit higher. So the evolution is that is due to the inspiral phase as f to the 2/3. In red, you have it's for binary neutron stars, so they are at higher frequencies because the masses are smaller. And in green, it's for binary black holes. The uncertainty is essentially due to the uncertainty on the rate. And because we have more detection for binary black hole, we have the expected rate, the rate we have measured is more precise. So this is what we obtain: 2.1 10 to the minus 10 for binary neutron star and 5 10 to the minus 10 for binary black hole, which is of the same order of magnitude. And below 100 Hertz, they are both evolving with f to the 2/3. So it's very difficult in the frequency domain to distinguish between the binary black hole background and the binary neutron star background. But it's very different in the time domain. And the time domain is also a way we can use to distinguish between astrophysical background and cosmological background. So here I have shown the time series in red for binary neutron stars and in green for binary black holes. And there is this quantity we call the duty cycle, which is also the average number of sources that are present at a given time. So this quantity tells you whether the sources overlap or not. And for binary black holes, they clearly don't overlap. You have one source and a long time of silence between the sources. For binary black holes, it's a bit different. There is what we call a continuous background, meaning that in the time domain, you always have a source present. But if you look close, you see that it's not what we expect from a Gaussian background. The amplitude at a given time is not given by a Gaussian distribution. And this background is not Gaussian because even if you have at least one source present at all times, you don't have enough sources overlapping to have a Gaussian probability of the amplitude. And that's a way we can use to distinguish this astrophysical background from the cosmological one. And also to distinguish between binary black holes and binary neutron stars. Okay, so when I gave the definition at the beginning of the stochastic background, I said that it resulted from the superposition of a large number of independent and unresolved sources. And there is a subtlety here with the term unresolved. When people thought about the stochastic background first, they were thinking about the cosmological background, so background that is Gaussian. And there are so many sources arriving at your detector that even if you have a perfect detector, you will never be able to separate them. But we don't have perfect detectors. So the background is also created by sources that are not detected individually, even if they don't overlap. So it means that depending on the sensitivity of the detector for this kind of background, the background is different because what we are looking at is the sources that are not detected, so what we call the residual background. And when we prove your sensitivity, you are going to detect more and more sources, and you are going to decrease your background. So if we have this definition, the astrophysical background is not really a true background because it depends on the sensitivity of the detector, which is not the case for the cosmological background. And we can hope that improving the sensitivity, we can reduce and maybe one day subtract this background to see the cosmological background below. So here is a calculation I've done for what we predict at the moment for the background, adding together binary neutron stars and binary black holes. The total background is in black when you have all the sources. The residual background for second generation detectors, so first only Hanford, Livingston, and Virgo in continuous blue, and in dash blue you had LIGO, India, and Kagra. I don't know why I forgot the I here. So there is a small decrease of the background. And there is again a small decrease for what we call the A+ sensitivity, which is after design sensitivity. And you can see there is a real decrease for 3G detectors, like about 1 or 2 orders of magnitude for Einstein telescope or Einstein telescope plus 2 cosmic explorers. This residual background is essentially the background from binary neutron stars because we see better binary black holes. And there are papers showing that we should be able with Einstein telescope and 2 cosmic explorer to completely subtract the background from binary black holes. So now I'm going to, in the last minutes I have, I'm going to talk about the data analysis method we are using to search for this stochastic background. So we search for an excess of coherence in the cross-correlated data from 2 or more than 2, 3, 4 detectors. And we don't have real assumptions about the morphology of the signal. We have this assumption that the background is stationary and polarized, isotropic and Gaussian, because the method was developed for the cosmological background. We have checked that if the background is not Gaussian, it doesn't really change anything because we work in the frequency domain. We have other methods to search for isotropic background I'm not going to talk about today. So when we do the cross-correlation product, because in each detector we have a contribution from the noise and a contribution from the signal. And when we do the cross-correlation product, we eliminate the part that is due to the correlation of the noise because we assume that the detectors are independent. The gravitational signal and the noise in detectors are uncorrelated too. And we end being able to recover the cross-correlation product of the gravitational signal only. How do we do that? We work in the frequency domain and we calculate this cross-correlation product. S is the signal in each, the Fourier transform of the signal in each detector, and Q is an optimal filter that is constructed using the noise, P1 and P2 in each detector, a template, that's the only assumption we have, a template for the omega, which we assume is a power law, and gamma, which I will talk about that in the next slide, is the overlap reduction function. The average value of Y is giving an estimate of omega, and the variant an estimate of the noise. And the signal-to-noise ratio, that's important, evolves with the square root of the observation time. So the overlap reduction function characterizes the loss of sensitivity that is due to the separation and also the relative orientation of the detectors. So here are some examples. In red, it's for the two LIGO. So at higher frequency, you start to really lose sensitivity. The signal-to-noise ratio, as I said, evolves with the square root of the observation time. And in order to have an idea of the sensitivity to a stochastic background, the same way we have sensitivity curve for individual sources, we define the power integrated curve that you can see here. And what's important, the only thing you have to remember is that if the spectrum crosses like here, or simply is tangent to the curve. So if it's tangent to the curve, it means that it could be detected with a signal-to-noise ratio of 2 after 2 years of integration. And 2 years of integration means 1 year of data, because we assume 50% duty cycle. So that's how we do the analysis. We split the data into 192 segments. There is downsampling, hand windowing, high pass filter, and then the data are fast Fourier transformed. And then we remove time segments where the noise is non-stationary that can corrupt the analysis. And we also remove bins of frequencies that display high coherence between the detector or with auxiliary channel. For example, the magnetometers. And okay, the rest is not very relevant for this presentation here. So here are the constraints we obtain with like Overgo and Kagra with the third run. So we don't have any detection. There is no evidence for a stochastic background, but we were able to put upper limit on models with different power spectrum. The 2/3 is the one related to the background from compiled binaries, and 0 is what we can expect for cosmic strings, for example. So thanks to that.
Sorry to interrupt, you have 5 minutes.
Yeah, thank you. So we were able to put constraints on cosmic string model. So I'm not going to speak about that because there have been a presentation by Daniel Steers. So this the O3, O2, O1 data were used to constrain 3 different models. That the stochastic background gave the best limit for 2 out of 3 of these models. And there is also a paper, a short author-length paper by people in the collaboration about constraining phase transition. And again, it's upper limits. So for these models, they have been using broken power laws. So not just one power index, but 2. And the frequency is related to the temperature, where the slope changes is related to the temperature. There is also a search for extra polarization. So the difference in the search I have been described until now, we are just using the plus and cross polarization. If we add other ones, we just have more, we have a sum here. And for each polarization, we have a different overlap reduction function that can be calculated. And after that, the search is exactly the same, just that we use different overlap reduction function depending on the polarization. And again, so after there is a Bayesian analysis. So we first test whether the results are more in agreement with noise only, or if there is a stochastic background. And in case there is a stochastic background favored, we looked at whether it's more likely that it's tensor polarized, or if there is more evidence that there is other polarization. And again, we have obtained constraints, not detection, but constraint on extra polarization. So to conclude, I would say that the stochastic background can probe the physics beyond the standard model through the contribution from inflation. I have mentioned enhanced contribution compared to the slow roll inflation model, cosmic strings, phase transition, and primordial black holes. There is what we can also look at in the stochastic background is a signature from extra polarization. And before we can do all these things, there is this astrophysical foreground that is expected to mask the cosmological background, and we need to find a way to remove it. So I will stop here.
Okay, thanks very much. Yes, you have extra 2 minutes if you want. So we have no questions on the chat. So if anyone has any questions, please just unmute yourself and ask. I also see no hands raised. Well, we still have nothing.
Okay.
Well,
I can just mention that we have also a search for a non-isotropic background. So we just release the assumption of anisotropy, and where the search again, we have model for anisotropies. That's, for example, a nice model simulation of what we could have from the background from binary black holes, binary neutron stars, and it's less. There are also models for the one from cosmic strings, but it's less than that. And that could be also a way to, of course, to distinguish between astrophysical and cosmological backgrounds. And that's a result from the LVK collaboration on that.
Thanks very much. We still have no question. Now we have a question by Mark in March. Please go ahead, Mark.
Yeah, thanks very much for a very, very clear talk. Can I ask something a little bit nerdy? You kind of skipped over it a bit. The method for the power spectral estimate. I just wondered if you could sort of talk about the things that you skipped over, and perhaps a little bit more of the reasons for the choice. You know, why the Han window, and what was the overlap, and that kind of thing. Yeah.
Why we chose the Han window, it didn't come like that. We have tried, first we were analyzing using Turkey windows. It's not, the Han window is, if you use a Han window, which is a Gaussian, you are going to lose too much data. So what we are doing now is overlapping Han windows. And that's what we had been testing with simulation, and that is the one that is giving the best results.
Is that with what amount of overlap?
50%.
Okay, there was a couple of other things on that slide that I wanted to ask about.
Okay, which? This one after, maybe. No.
It's
this one.
Yeah. Yeah, so the coarse graining. What's the choice? 0.03 of a hertz.
Okay, that's again. So before we were using 0.25, and with 0.1 data we had many lines, and in order to identify them, we needed smaller bins. The thing is that with smaller bins, we need longer segments. Okay, before we had 60-second segments, I think, and then we had 0.25 hertz. And then we changed because of these slides. We wanted to be able to remove. The thing is that when we have a longer segment, as you see, we are throwing away some segments. So each time we prefer to throw away a 60-second segment that's a 192.
So when you coarse grain, I can't do the sums in my head, but when you coarse grain the 192-second downsampled segments to 0.03 of a hertz, how many different individual frequencies get put into this bin? If I understand.
We have not done. I don't remember what frequency range we used for the. For O3, to be honest.
Okay.
It's something like 200 hertz.
Okay.
We always analyze between 10 and a bit less than 200, so sometimes it has been 175. And it's not necessarily the same for the different power index, but I can just have a look at the paper.
Well, I think I've
I'm sorry, I don't
used too much of the question time on these very detailed questions.
It's not. I know it's about this. I should have put that in the slide because I never remember.
Yeah, thanks.
Okay, so there's no other questions, so I think we can move on to the next talk. Thanks very much, Tanya, for your last talk. The next speaker is Naoki Seto from Kyoto University, and he'll talk to us about DECIGO. Please go ahead. We can see your screen and your cursor too.
Can you hear me?
Yes.
Okay. Okay, first I'd like to thank organizer for inviting me to this interesting workshop. I'm Naoki from Kyoto University, Japan. I will start my talk with this slide showing noise spectra of various detectors. So this axis shows frequency, and this axis shows strain sensitivity. And this black curve is a typical noise spectrum of current generation detectors such as advanced LIGO and advanced Virgo, sensitive around 10 Hz to 1000 Hz. And this black curve shows the design sensitivity of LISA, sensitive around 0.1 MHz to 100 MHz. And Chinese mission, TAIJI will have similar sensitivity to LISA. And another Chinese mission, Tenkin, will have a slightly higher frequency than LISA and TAIJI. And between LISA band and ground-based detector, this red curve shows the design sensitivity of DECIGO. Sensitive around Hz, I mean 0.1 Hz to 10 Hz. And this black curve, similar to this red one, is the sensitivity curve of BBO. Even though the sensitivity curves of BBO and DECIGO are quite similar, the basic design, interferometer design is quite different. For DECIGO, we are planning to use Fabry-Perot type interferometer, similar to ground-based detectors. But for BBO, the detector design is similar to LISA, I mean optical transponder type interferometer. In my talk below, I will first discuss detector aspects of DECIGO, and then discuss its scientific targets. Actually, I'm mostly working on theoretical things, so in order to explain the detector aspects of DECIGO, I will use slides from Seiji Kawamura, who is PI of the DECIGO project. In this slide, I will briefly explain why we will use Fabry-Perot cavity, not LISA-like transponder type interferometer. And this figure shows fundamental noises of various potential detector configurations. This axis shows frequency, and this axis shows strain, only showing the basic fundamental noises such as radiation pressure noise and shot noise. And this green curve is a typical noise spectra of LISA-like transponder type interferometer, this type interferometer. So low frequency is radiation pressure noise, and this part is shot noise. And this corner frequency is determined by the arm length of interferometer. And above this frequency, the gravitational wavelength is shorter than the arm length. So we have signal cancellation like this. And anyway, in this kind of transponder type interferometer, the arm length is much longer than the so-called Fresnel distance, characterizing the wave effect. And the receiver can get a tiny fraction of emitted photons. So high frequency part is limited by the small numbers of detectable photons. So in order to increase the photon number and suppress the shot noise, we shorten the arm length like this, from this point to this point. I mean the arm length similar to the Fresnel distance. So basically receive all the emitted photons and suppress the shot noise from original position to this position. And also using Fabry-Perot cavity, we will finally get noise spectrum like this. So low frequency part is determined by radiation pressure noise, and this part is shot noise. And actually in this figure, I only show the fundamental noises, but we also have a practical noise such as acceleration noise. Acceleration noise related to the strain fluctuation like this. The strain is basically positional information, so we make time integration twice to get positional information, and divide this thing by the arm length to get non-dimensional quantity. But in order to keep strength fluctuation to a certain level, so we must suppress acceleration noise or proportional to the arm length. But arm length is much shorter in this case. I mean, DECIGO diaphragmator. We will have more stringent acceleration noise requirement for at low frequency part. Because L is short, we have to suppress acceleration noise to get small string fluctuation. So this, I mean, stringent acceleration noise requirement and beta short noise limited sensitivity at high frequency part is important aspects of DECIGO type interferometer. And in this slide, I show the pre-conceptual design of DECIGO. Its arm length is 1,000 kilometer, but the arm length of LISA is 2.5 million kilometer. So the arm length of DECIGO is about 3,000 times smaller than LISA. And this is a roadmap of DECIGO. Actually, the most important information here is missing in this slide, but hopefully this is around 2030. And before realizing DECIGO, we will have a precursor mission called DECIGO, like this, whose sensitivity is about 10 times worse than the final DECIGO. So anyway, we will planning to have a precursor mission before DECIGO, whose sensitivity is about 10 times worse than the final one. This slide shows orbit and constellation of DECIGO. We are planning to use 4 units. So each unit is composed by 3 spacecrafts like this, forming a nearly regular triangle. We will use 1 unit here, 1 unit here, and 2 units here. And these 2 units will be used for making correlation analysis for detecting weak primordial background. Even though the previous speaker already discussed the correlation analysis, I will also briefly discuss correlation analysis later in my talk. And these 2 separated ones will be used to realize good sky localization for individual astrophysical sources by taking long baselines, and also remove blind angle for cosmological compact binaries. Because in order to detect weak primordial background, we need to subtract the strong foreground composed by cosmological binaries. And for identifying and subtracting their signals, we need to remove blind angles for cosmological binaries. So these 2 will be used for making good sky localization and also remove blind angles for cosmological compact binaries. So now I will discuss scientific targets of DECIGO, and this is outline for the rest of my talk. I will first stochastic gravitational wave background, briefly explain primordial wave background, and also briefly discuss the technique correlation known as correlation analysis. And then I will move to cosmological binaries such as stellar mass black hole binaries and binary neutron stars. I will explain the foreground subtraction problem and also discuss that these binaries can be used as a powerful scientific tools for cosmology and astrophysics and also physics. And actually, DECIGO band, I mean 0.1 Hz to 10 Hz, is suitable for observing gravitational waves from intermediate mass black holes. But since I do not have time enough, I will skip this interesting topic today. So stochastic gravitational wave background from our universe. This figure shows the history of our universe. This is today, and this is very early universe. As you know, gravitational interaction is very weak, so gravitational waves have extremely high permeability. So therefore, if we can observe gravitational waves from a very early universe, it can be regarded as a very important fossil from the early universe. And one of the most important objectives of DECIGO is directly observe this important fossil as a wave oscillation. And by carefully studying this important fossil, we want to understand the generation process of the background and also get information of our universe after the generation of the background. And actually, we have a strong candidate for the prime model background, that is gravitational waves generated during inflation. I will explain more about the inflation background in the next slide. And this figure shows a typical present-day inflation background spectrum as a function of frequency, and this axis shows a normalized energy density, omega GW, as discussed by previous speaker. And these spectra are mainly determined by two elements. First element is related to generation of the prime model background, and in the case of inflation, it's the inflaton potential, shape of the inflaton potential. And the second element that determines the shape is a transfer function that is closely related to the cosmic history. And the CMB mode observation probes gravitational wave background at very low frequency regime, around 10 to minus 17 Hz, close to the inverse of the age of the universe. And actually, this observation is a very good probe of the element A. Since we know the relatively low redshift universe relatively well, G less than 10 to 4 or 10 to 5. So this CMB observation is very good probe for the element A, inflaton potential or something like that. But with DECIGO, we are planning to observe gravitational waves around 0.1 Hz. This is a good probe of both A and B. So even though these two observations are largely different in terms of frequencies, like 10 to minus 16 times difference, but these two observations are complementary. By carefully studying these observations, we might get information of A and B somewhat separately. So these two observations are mutually very important. So I will briefly explain correlation analysis for detecting weak background. Even though the previous speaker already discussed this thing, I will briefly discuss about the basic idea. The basic idea is create two noise-independent detectors. Well, let us consider this kind of situation. So we have two interferometer 1 and interferometer 2. And assume that their separation is much shorter than gravitational wavelengths. So in this case, so we can regard, and if the orientations of two detectors are nearly same, they will feel almost the same signal, same response to gravitational wave background. So in terms of the, in this case, the overlap reduction function, as previous speaker said, is close to unity. Gamma is close to unity. So anyway, in this kind of situation, the data stream of detector 1 is written like this. So H is a response to the gravitational wave background, and N1 is the instrumental noise of detector 1. And similarly, data stream of detector 2 is written like this. H is a response to the background, and N2 is instrumental noise. And we assume that N1 and N2 are statistically independent. And we take product of these two data streams and get 4 terms like this. So this is signal term, and this is noise, and this is cross correlation of noise and signal terms. And these 3 terms are basically random walk type noise. So if we take long integration time, the amplitude of these 3 terms is basically proportional to square root of integration time. In contrast, this is a coherent term. So this one is basically proportional to integration time. So by taking long integration time, we want to suppress the noise term relative to the signal term. And we can improve the sensitivity as a function of integration time like this. But the important point here is that we cannot make correlation analysis only with a single triangle unit. So actually, we can make two noise-independent data streams whose response is similar to the interparameter like this, geometrically like this. But due to the geometrical symmetry, we cannot detect isotropic background with single triangular unit. Due to the symmetry, the contribution from the isotropic background will be exactly cancelled if we only have a single interparameter, single triangle unit. So this is the reason we prepare two triangle units to make correlation analysis with DECIGO. So with DECIGO, by combining two triangular units and make correlation analysis, so you want to detect weak background, weak primordial background as weak as 10 to minus 16 after integration time of 5 to 10 years. Now I will discuss gravitational waves from cosmological compact binaries such as stellar mass black holes and binary neutron stars. First, I discuss foreground subtraction problem, and then discuss that we can also use them as a powerful science tools. Actually, the foreground subtraction problem around 0.1 to 1 Hz was first discussed by Cutler and Harms 15 years ago from now. So this figure is from their paper. This axis shows frequency, and this axis shows strain noise amplitude. And this black curve is a noise spectrum of actually BBO. And by correlating these two interferometers with this specification, we can detect, detection limit is somewhere around 10 to minus 16 after long-term integration order of a year. But this upper black line is a foreground made by cosmological double neutron stars. Each double neutron star sweeps the DECIGO band in the time scale of a year. But when we sum up all of their contribution, we get kind of stationary foreground like this. And the magnitude of the foreground is, let's see, about 10 to 4 times stronger than the detection limit by the correlation analysis. But we know much about the binary merger event after the first detection. So the DNS rate is 3 times higher than the estimation by Cutler and Harms. So the foreground, is 3 times higher because the foreground is proportional, roughly speaking, proportional to rate times mass of this power. And also, now we know that many binary black holes merge in our universe. So the typical mass is 30 plus 30 solar masses, and the estimated merger rate is something like this. So the foreground made by binary black holes is like this. So in total, 30 times larger than the estimation in 2006. So foreground become much stronger. The estimation of the estimated foreground become much stronger after the detection of many merger events. In this slide, I will briefly discuss binary subtraction problem. First, I will compare the data amount. And the number of fitting parameters per year is estimated like this. So we have about 10 fitting parameters for each binaries, like 2 masses, sky directions, some parameter related to spin, distance, and so on. And the merger rate is typically 10 to 5 per year. So in total, we need 10 to 6 parameters per year. but the number of available data is estimated like this, assuming 1 Hz sampling and 1 year is 3 times 10 to 7 seconds. So the number of data amount is 3 times 10 to 7 per year. So this number is larger than this one. So we can basically make, we basically have sufficient data amount. Another aspect for possibility of the binary subtraction is signal to noise ratio and rotation cycle. And roughly speaking, with a coherent signal to noise ratio is proportional to redshift, weakly depend on the redshift at high redshift like this due to a cosmological effect. And also rotation cycle becomes smaller at high redshift if we fix observational band, for example, 0.1 Hz to 1 Hz, because of the also cosmological effect.
Sorry to interrupt. You have 5 minutes.
Okay, sure. So the difficulty of detection is a combination of this effect and this effect. So the detection is supposed to be most difficult at intermediate redshift, for example, z equals 1 or so. And with current DECIGO will have nearly or sufficient sensitivity for detecting all the cosmological binaries. So finally, I will discuss that individual binaries can be also used as powerful science tools for physics, cosmology, and astronomy. As I already mentioned, the DNS rate is, for example, 10 to 5 per year. And these binaries must be identified and subtracted for detecting weak parameter background. But these binaries has a large number of cycles characterized by small number of fitting parameters. So these binaries can be regarded as very accurate clocks characterized by small number of parameters. So we can use large number of binaries to examine theory of gravity. And also with this kind of DECIGO-like configuration, we can realize good sky localization. Sky localization is basically determined by this combination, gravitational waves divided by the baseline. But this combination is like 10 to minus 3 for gravitational wave of 1 Hz. So we can realize very good sky localization with this kind of detector network. And also only with gravitational wave, we can estimate the luminosity distance. So by identifying host galaxy and determine the redshift by electromagnetic observation, we can, for example, constrain dark energy parameter very well. So let me summarize my talk. So DECIGO is Fabry-Pérot type interparameter, short arm length, so large number of photons, but we have stringent requirement on acceleration noise. I discuss scientific targets, parameter background, and individual compact binaries. Okay, I will stop here. Thank you for your attention.
Thanks very much for your very nice talk. We have no questions on this chat. Let us see if someone wants to ask something. Yeah, we have John Ellis. Please go ahead, John.
Okay, thank you. Thank you very much for that nice description of DECIGO. Perhaps you could describe in a bit more detail what's the planned schedule for the various different stages of DECIGO, and also what is the status of approval for DECIGO?
Would you say, so the second part is okay, so let's see. So I think this slide. So at present we have some kind of let's see. So your question is about current status, and what was your second question?
Well, you only have one date there. It's not clear to me what the horizontal scale is. So when
this is one resolution is 1 year, 2 year. So hopefully, so this is like 2040 or something, but situation is quite unclear now.
And to what extent has the DECIGO program actually been officially approved?
Well, Japanese Space Agency, JAXA, is supported some preliminary missions, but not B DECIGO and DECIGO are not currently accepted. I mean,
Okay, well, let's hope it gets confirmed.
yeah.
Are there any other questions? Yes, we have one from Marek. Please go ahead.
Yeah, it's a similar question, so we can stay on the same slide.
Mm-hmm.
Because you also mentioned ultimate DECIGO, but it's not on the timeline.
No. This is not the ultimate one. This is a more conservative one. Standard DECIGO. So actually, previously we will have we were supposed to have DECIGO Pathfinder, but this is basically technology demonstration mission, and JAXA did not approve this kind of mission, so we will slightly change the schedule to prepare B DECIGO that will have that we can do astrophysics. I mean, detect, for example, binary neutron star at Z equal at distance of 200 megaparsec or so. Let's see. So this one is not ultimate DECIGO, but this one is standard DECIGO.
Yes. So where would ultimate DECIGO be on this timeline?
It's far future, so I did not show the ultimate DECIGO. Yeah.
I see. Thanks.
Are there any more questions? I don't see any. So thanks very much again.
Thank you very much.
It was a really nice talk. We can then move on to our next speaker, Francesco Muia from the University of Cambridge, and he's going to talk to us about ultra-high gravitational wave detection. Yeah, they can see your slides and your cursor.
You can see everything? Okay.
Yes.
Okay, great. So thanks a lot for being here, and thanks, many thanks to the organizers for the invitation. Just a little warning, I've had some connection problems these days, so if it disconnects, don't run away. I'll just restart the router. It takes just 1 minute. Okay, so this talk is basically on the outcomes of a workshop that we organized back in 2019 in Trieste, focused on high-frequency gravitational waves. And one of the outcomes of this workshop has been a review paper that we had in November. And that was the result of a large collaboration of more than 20 people. So following this paper, I will try to illustrate what is the state of the art of high-frequency gravitational wave science, and to illustrate the science case and what are the prospects for the future. Okay. The interest in this topic starts from a simple observation, which is that non-astrophysical objects can emit gravitational waves only below a benchmark value, which is roughly 10 kilohertz. And this comes from the fact that you can associate a natural frequency to a self-gravitating body, and the size of the body is bound by the Schwarzschild radius. So this simple observation has profound implications, because it means basically that if you are able to detect gravitational waves frequencies larger than this benchmark value, then it must be a cosmological source or some beyond the standard model physics source. Okay, in the first part of the talk, I will illustrate the kind of sources that you can have in this frequency range, and then I will talk about the experimental part. In terms of sources, so you can divide them into early universe and late universe, of course, and I will start with the late universe ones. We have identified a few possible sources in the late universe, among which subsolar primordial black hole mergers, exotic compact object mergers, and superradiance. And of course, all these sources give different ways of probing beyond the standard model physics. I won't have time to go into the details of all these sources. Let me just spend a couple of words about superradiance, which is you get superradiance when you have a light scalar field surrounding a rotating black hole. So when the quantum wavelength of the axion is of the same order of the Schwarzschild radius of the black hole, so that you get this relation between the mass of the axion and the mass of the black hole, then superradiance can happen. And so basically, an axion cloud is formed around the rotating black hole. And this axion cloud, on the one hand, it extracts rotational energy from the black hole. And on the other hand, it can lose energy into gravitational waves. And it can lose energy in different ways. For instance, axions can annihilate into gravitons. And you see the frequency is set by the mass of the axion. And for a black hole with a mass around the solar mass, we are talking about frequencies around 100 kilohertz. It's interesting that this is a long-lived monochromatic source, so it's peculiar. And the characteristic amplitude is given by this expression. Here in this slide, you can see a summary of the sources in the late universe that we have collected in our paper. You see that the benchmark value for the characteristic amplitude is around 10 to the minus 20 in the region between 1000 Hertz and 1 megahertz. Okay, let's go now to the cosmological sources. Before going to the details of the possible sources, there are a few things that are model independent. First of all, the characteristic frequency, we have heard this already a few times. Due to causality, basically, we know that the gravitational wavelength at production has to be smaller than the horizon size at production. And this means that you can write the frequency of the gravitational wave that is produced in terms of the temperature at production. And this epsilon parameter parameterizes basically the ratio between the wavelength and the horizon size. And it must be smaller than 1. Now, taking this value to be 1 for the sake of simplicity, you can see what are the energies that we are talking about. So basically, everything that happens at energies, temperatures above 10 to the 9 GeV is beyond the LIGO range. So you see that there is quite a lot of interesting physics that can be learned at high frequencies beyond the LIGO range. And of course, another model-independent characteristic is that gravitational waves produced in the early universe produce a stochastic background, while for the late universe sources, one might get a coherent signal. Since we are talking about cosmological gravitational waves, we know they are better described in terms of omega, the fractional energy density, and the relation between omega and the characteristic amplitude of the gravitational waves given by this expression. Now, putting in numbers here, you see that h scales as 1 over f, which means that for a given value of omega, it's harder and harder to detect gravitational waves at a larger frequency. So for instance, taking the benchmark value from LIGO 10 to the minus 9 at 100 Hertz, this corresponds to a strain of 10 to the minus 25. When you go to the gigahertz, this goes down to 10 to the minus 32. And we have to recall, of course, that since the gravitational waves redshift as radiation, we have bounds coming from CMB and BBN that in terms of omega, it's just omega has to be smaller than 10 to the minus 6. That translates into this expression for the characteristic amplitude. That said, there is a bunch of possible sources in the early universe that can give rise to gravitational waves at high frequencies, most of which we have already met during this workshop. For instance, some of the production mechanisms during inflation include extra species, and Emanuela yesterday or 2 days ago talked about some of them. Then we have modified gravity and second order scalar perturbations that we have already heard about. But then there are also production mechanisms after inflation, of course, among which, for instance, phase transitions, strings and effects, cosmic gravitational microwave background. I won't go into the details of all these sources. Let me just say a few words about my favorite one, which is preheating and oscillon. We know that after inflation, of course, the energy density stored in the inflaton needs to be transferred to the standard model degrees of freedom. If there is some non-perturbative effect involved in this process, then we are talking about preheating. And there are various ways in which this happens. The simplest example is when you have a self-resonance of bosons. And this can happen in different ways. For instance, one can put the scalar field perturbation equation in the form of a Mathieu equation, and can show that there is some resonance bands. For instance, if you're in this region of the unstable chart, Mathieu chart, you get a narrow resonance, which is quite slow growth of the perturbations. But also you can have tachyonic effects. For instance, when you have the omega squared in the equation for the perturbations, it becomes negative. And in these cases, typically the preheating happens very fast. Here, for instance, I'm showing you a couple of simulations that we did a few years ago, but related to string models. Here you see the narrow resonance, which is quite slow, while this corresponds to tachyonic effects. And here we got frequencies around 10 to the 8 Hz with an amplitude around 10 to the minus 9. And these numbers are quite typical, as you can read, for instance, in this paper by Dani and Francisco. Okay, here's a recap of the possible sources from the early universe. And you see that here the benchmark value for the characteristic amplitude is around 10 to the minus 30. And beyond the ones that I mentioned, there are many more possible sources that give a signal at high frequencies. You can read about this in our review and find all the proper references. So I hope I convinced you that there is a lot of physics that in principle can be learned by exploring gravitational waves at high frequencies. And we could add some interesting entries to this table, which is the quick roadmap. Okay, after having talked about the sources, let me say a few words about the experimental part. Let me also warn you that I'm not a detector person, so if you want to have more details, I encourage you to visit our the page of our workshop and see the talks that are stored there. The first obvious observation, which is crucial, though, is that since we are talking about high frequencies, typically the length scales that are involved are much smaller than the ones that we are used with the LIGO and the other detectors. And this means that it's not inconceivable that we could have tabletop experiments probing high frequency gravitational waves. The experimental situation is a bit confused because there have been many isolated attempts to build the detectors at high frequencies, but very often these were put only in the form of theoretical papers with no serious discussion about the possible sources of noise. So there is a lot of work to be done in this direction, and I will try to tell you about some of these. So first of all, interferometers don't seem to be the right way to go at high frequencies because of shock noise that grows there. One interesting implementation of the resonant mass idea is given by bulk acoustic wave devices that are developed in the group of Mike Bar at the University of Western Australia. So in these detectors, basically these cavities which is made up of quartz, has some vibrational modes that are excited and can give rise to a signal when a gravitational wave is passing through. And they are very small, you see, 3 centimeters and inexpensive, but still they are quite efficient. And they are sensitive in the megahertz to gigahertz range. And you see, they reach the spectral density sensitivity around 10 to the minus 22. And it's interesting that this group of Mike Tobar is testing these detectors. They have a first version. And you see, this detector has been running for 153 days, and they had 2 strong events reported last year. And even though there is no definitive conclusion about claim about the origin of these events, it's still good that they are trying to improve these detectors. So, for instance, in the second version, they are planning to place some muon detectors to exclude, for instance, cosmic rays, and they are planning also other improvements to improve this concept. Next one, different idea, but very interesting, is about levitated sensors that are developed mainly at in the group of Andrew Geraci at Northwestern. Here, the idea is that you have a cavity with a standing wave inside, and a dielectric nanoparticle can be trapped using basically radiation pressure at the antinode of one of the antinodes of this standing wave. And when and the potential that the nanoparticle feels is proportional to the electric field, so it's highly tunable, the frequency associated to this potential. Then when a gravitational wave goes through the cavity, basically what it does is that it displaces the nanoparticle with respect to the trap minimum, and the displacement, of course, is proportional to the gravitational wave amplitude. And then basically you have a driving force for the nanoparticle that if the trapping frequency matches the gravitational wave frequency, then there is a resonance, the gravitational wave can be detected. Here the problem is that the fundamental limitation is thermal noise. You see, since this is the minimum sensitivity that you can reach, you can improve the detector either by lowering the temperature, or using larger masses, or using longer cavities. And these detectors are sensitive in this range, around 100 of kilohertz. And you see in this paper, these authors have proposed to use a stack of dielectric disks to have heavier particles. And there are also improvements that are planned. They're building a 1 meter prototype, but then they have planned already to build a 10 meter and 100 meter prototype. And this concept is tailored to explore primordial black holes and especially super radiance around the 100 kilohertz region. Okay, last idea that I want to tell you about is magnetic conversion. Here, the idea is very simple. You can basically convert a graviton when it goes through a static magnetic field, even though you can describe this process completely in a classical way. So if you have a static field in this region, a static magnetic field in this region, a gravitational wave goes through, basically what it does is to stretch and squeeze the field. So using a Maxwell equation, you see that you have an electromagnetic wave that is generated. And since here you see the electric field is proportional to h, the power flux density will be proportional to h squared. And putting in numbers, as Andreas has done in his recent paper, you see that if you go around the gigahertz region, still you get very few photons actually. So this idea has been used to put bounds on gravitational waves at high frequencies using data coming from light shining through a wall experiments. Because in those experiments, what you have is basically a photon that goes through a static magnetic field, is converted into an axion, goes through the wall, and then gets converted back into a photon. Now, if you just ignore the first part of the experiment, you can use the second static magnetic field to put bounds using this magnetic conversion on gravitational waves. And these authors put bounds in these frequency ranges using the data from Oscar and CAST, and they also gave projections, prospects from these other experiments. Now, the point is to understand whether you can use a similar technology to put bounds in the gigahertz range, which is the most interesting for cosmological signals. And Andreas and collaborators have argued that you can do that, but still we have a gap, a technological gap, which is of about 6 orders of magnitude. There is also another proposal. I'm running out of time, but let me just tell you that this again uses the idea of magnetic conversion, but on top of what you have before, it also puts a laser beam in the direction of the gravitational wave propagation. And this basically leads to an electromagnetic wave that is propagating orthogonal both to the external magnetic field, which is in the y direction, and to the propagation of the gravitational wave direction. And if you are able to detect these photons in this orthogonal direction, you detect the gravitational wave basically. And the number of photons here is proportional to is linear in h, contrary to the previous result. Okay, then there are also other ideas in the solid state direction, but there is a bit of work to be done in that context. Let me just say that in the best case, in order to detect gravitational waves from the early universe, we have a 6 orders of magnitude technological gap. And here you can see the sensitivities compared with the sources. For the late universe sources, there is this region that is especially interesting with the levitated sensors, while for cosmological sources, we have still a gap. I haven't heard from about the 5 minutes, I hope.
Yeah, because it's now.
Okay. No, I just wanted to be sure that it's not disconnected. Okay, thank you. Okay. Yeah, I haven't talked about most of the detectors here, but you see that there is a gap here. This YAXO are the prospects for magnetic conversion, and there is 6 order of magnitudes. While if we were able to make the Libacker detector work, then we will be able to reach barely the BBN bound. But the point is that nobody so far, as far as we know, has ever tried to build the Libacker detector. Okay, so we shouldn't be too discouraged about this technological gap that we have, because if you think that in 73, when the Misner, Thorne, and Wheeler book was written, they wrote in the book that basically interferometers have so low sensitivity that they are of little experimental interest. It was just like an academic toy model for them at that time. And it took basically 50 years and 23 attempts between prototypes and actual detectors to get to the first detection in 2015. And on top of this, since astrophysical sources, astrophysical signals are guaranteed at low frequencies, we haven't had the same amount of effort at high frequencies. So there is room to improve. And given the enthusiasm that we had after the first workshop, we decided that it would be a good idea to have like a working group on this, with the idea basically of creating a network of people who are interested in this topic and are willing to push research in this direction, both from the experimental and the theoretical point of view. And these are the researchers who are involved at the moment. Of course, one of the goals of this working group is to facilitate the technology development that is needed. And we are doing so at the moment, trying to involve all the interested groups, collecting information about their current and planned technologies. So if you are interested, you want to contribute to take part in the process, please, there's this questionnaire that you can complete. Where we are collecting this information, and this information will be the basis for the next workshop that we are organizing in October this year. October and November, we are still discussing, and the main points of this workshop will be to discuss what are the most promising technologies to focus on. Since, as I said, most of the ideas that have been put forward so far are only in the form of theoretical papers, we would like to try to plan the construction of prototypes for these ideas, for instance, the Libacker detector. And then also another point is, of course, discussion about how to facilitate existing projects, such as, for instance, the bulk acoustic wave devices, or the levitated sensors. And then from the theoretical point of view, of course, we would like to sharpen even more the science case for high frequency gravitational waves. And again, if you're interested in this, you can find all the information in our webpage that is hosted at the moment in the website of the Stephen Hawking Center for Theoretical Cosmology. You just go there, click this button, you put your email address and your name, and you will be updated about the next steps of our initiative. And I think I'm done with this. Thank you.
Thanks very much. It was very interesting, and you actually saved some 2 minutes, and we were behind schedule. Let us see if there are any questions. For now, there's nothing on the chat, but we have someone who raised his hand. Is Subo? Please go ahead.
Hi, Francesco. Thank you for the very nice talk. I was wondering about this I think it's a Gernshtein, the effect where you can convert gravitons into. So using a strong magnetic field, how do you know that you've definitely detected a gravitational wave? And I mean, because I'm imagining also the Primakov, like if there's an axion in the universe, for instance, then you could have also seen an axion come through. So is there a way to disentangle the existence of any other lights?
Well, I guess for axions at the same time, you will see a decreasing. Let me see. You will also see an effect in the first part if you have this kind of setup, no? I think you will have like this signal will decrease, I guess. But of course, the signal of the electromagnetic wave here in this first part of the experiment. But you also have experiments that don't have this first part, no? That they just say have this region and they are looking for solar axions. So in that case, I wouldn't know how to disentangle.
Okay.
But I agree, this is something that probably should be. So at the moment, what they have done is just to put bounds.
I see.
These guys, they just took the data and put bounds at these frequencies.
Thanks. I have a very, very short follow-up, which was that you mentioned that there was a need of a 6-order improvement in sensitivity.
Yeah, of course. To Andreas' paper, yes.
Yeah.
This is the best we could.
Right, and the best meaning that this is sort of, if you're looking for gravitational waves at very high frequencies, presumably from the early universe, you come up against the BBN bound above that, right? So I'm just wondering, so could that technological requirement be less if somehow you had high frequency gravitational waves produced after BBN? There are mechanisms that.
Oh yes, for sure. No, for sure.
Bump up the signal there, then the sensitivity requirement gets less, right? I mean,
yeah. If you don't have that bound, then yes. So for instance, for the late universe sources, we don't have that bound, right? So the typical amplitude is much larger. Yeah,
so would a cheeky way of interpreting that being that, let's say you had some mechanism of generating a 6th order of magnitude enhancement of very high frequency gravitational waves and nothing else, we already have the technology to detect. Is that a very cheeky way of interpreting it? Yes. Okay.
Yes. Yeah. And also say, because that bound is actually on the integral, right? Then you exchange the integral for the integral, and then you put this bound on that is 10 to the minus 6. But if you have a way to generate a spectrum which is extremely peaked, then again you will evade that bound.
I'm going to email you later.
Okay, thanks very much. I see no other hands raised and we are behind schedule, so we better move on to our next speaker and to the other end of the spectrum. So our speaker will be Michael
Thanks a lot again.
Thank you. From the Max Planck Institute, and he's going to talk to us about PTAs. Please go ahead.
Yep, thanks. Let me just share my screen. Hope you can see that.
Yes.
Excellent, thanks. Yeah, just going to the other side of the spectrum and go into an experiment which is already running for 25 years or a little bit more even, which is about detecting low frequency gravitational waves by pulsar timing arrays. And I'm sure you have heard all about the idea, but the idea is actually very simple. It is basically putting such a ground-based detector LIGO into space and use not the travel time of the laser light between the mirrors, but actually the travel time of the electromagnetic pulses coming from pulsars and their arrival time on Earth to see variation in the expected arrival time compared to our expectation of a timing model. That is called a pulsar timing array because we're looking at an array of pulsars. But as I will show you also, there's a number of external noise sources which make that detection difficult and why it has taken so long. What we try to find is also, as a first signal, stochastic background, and the very nice first talk sort of gave already introduction to that. Our background is astrophysical. We're talking about, as I will show you in a second, supermassive binary black holes. And they would indeed produce a stochastic background. In the first instance, we also try to see single pulses, single sources. And but what we actually try to measure is what we call the Hellings's and Downs curve. We will try to see the correlation of arrival times from different pulsars in different directions on the sky. If the pulsars are related, located in the same direction on the sky, the signals will both arrive late, early in correlation. That's why we have a positive correlation coefficient. If it's a quadrupolar wave, then we would expect an anti-correlation about 90 degrees separation on the sky. That's why we have this dip here, anti-correlation, and then you get again some degree of correlation if they're at opposite part of the sky. And that's reflected here in this curve, which plots the pulsar separation on the sky and the expected correlation coefficients between the arrival time. So if you detect something like this, then you have detected low frequency gravitational waves directly. Similar diagram was already shown. So this is the gravitational wave spectrum. Pulsar timing arrays probe the nanohertz regime, and I'll explain you later why that is the case. In fact, there are ways of making efforts to detect slightly higher frequencies, and I'll come back to that later. As I mentioned, the sources we are trying to discover are supermassive binary black holes that are created by the merger of galaxies. In the current understanding, of course, of hierarchical galaxy formation, we have smaller galaxies merging to larger ones, and whenever that happens, you have the supermassive black holes in the center of these two galaxies forming a binary system. And depending on the astrophysical processes that actually make them come together, we expect that they would emit gravitational waves in a frequency range that is detectable with pulsar timing arrays. What would we expect is actually, again, a power law signal. Here's the characteristic strain. You would expect basically an amplitude and a power law dependency. And the power law index in this writing would be -2/3. But we know that astrophysical process that I already mentioned can basically modify the spectrum. For instance, you can have a low frequency turnover and that comes from environmental coupling, hardening, and so really ugly astrophysics that we don't quite know actually where the signal, how the spectrum really looks like. It could be a power law, but there could be deviations from it. And actually measuring the spectrum gives you some nice, interesting constraints on the astrophysics. But it may be actually better to observe at slightly higher frequencies. And again, I come back to that later. There are basically three major efforts ongoing in the world right now to detect monohertz gravitational waves. There's the European Pulsar Timing Array in Europe, also the large European array of pulsars deploying, and I'll talk a bit more about that. But essentially, it's the five biggest telescopes, 100-meter class telescopes that we have in Europe, looking for the signals. Then we have in North America, the Nanograph timing array, which used to use Arecibo and still use the GBT. And on the Australian side, looking at the Southern Hemisphere, we have the Parkes Pulsar Timing Array using the Parkes telescope so far. We compete, I have to say, but we also collaborate in the International Pulsar Timing Array. We had a first International Pulsar Timing Array data release in 2016, where we had 49 millisecond pulsars with typical cadence of 1 to 2 weeks, and the legacy data sets today spent back 25 years, and I come back to that. Actually, you may have seen it on the archive. All PTAs have seen a common red noise process. I'll just briefly comment on that because I think we still don't know exactly what it is. So there's no detection yet. I think that has to be stated very clearly. But what all the PTAs say is what we call a red noise process. So we see some correlation, but we haven't seen a Hellingsen down curve yet. So the EPTA paper of that is about to be submitted. Here we have 6 pulsars with very high precision data going back 25 years. I want to explain, these are the timing residuals. I won't go in detail in explaining them. Let me just show you the plots, and I'm not sure why the quality is so bad in the PDF files that I provided. The quality is better. But this is the spectrum that we fit from the EPTA data. And this is the amplitude and the spectral index. And the spectral index expected, in this case, energy density, it's actually consistent with the index that we would expect from a gravitational wave background. We had seen the signal actually already a couple of years ago in the first data release. We didn't publish it because we didn't quite know what it is, and we were not sure, we still don't know what it is. But so the yellow contours here was from the DR1, and the new data is more or less confirming what we saw at the time, but I think we still don't know what it is. We can compare this with what Nanograph sees. The error bars are still large, but essentially I think we do agree on essentially the features of the common red noise signals. But again, we don't really know what it is. It could be a hint of gravitational waves, but it could also be something completely different. There's a nice work by the Australian colleagues who show that if the pulsars have some intrinsic noises which is similar, which is not completely impossible, it may mimic such a signal, or it could be other extrinsic non-gravitational wave noise sources in our data. And one of them is, of course, the interstellar medium, because the pulsar signal has to propagate through the interstellar medium, which is ionized and magnetized, and it's certainly not uniform. So you have lots of different interstellar weather. The easiest to think of is, of course, variation in the so-called dispersion measure, which is the electron column density, which has an impact on the arrival times, frequency dependent. We usually try to compensate that with multi-frequency observations, but it's not completely impossible that we have some residual effects that we are not having accounted for. There are also effects of the solar system ephemeralities, because we have to reduce our data to a hypothetical arrival time at the solar system barycenter. For this, we have to know the exact position of the planets in the solar system. These are known to some precision, but not maybe necessarily to the precision we need. And there can also be residual effects of simply not knowing what the locations of the planets are. In fact, we are sensitive now also to asteroid masses, so it is getting complicated. One effect that has been completely neglected so far, and we pointed it out in a recent publication, is that apart from dispersion measure variation, there's also variation in scattering. Scattering is the result of multipath propagation in the inhomogeneous interstellar medium. So we have a wavefront that is distorted by the inhomogeneous interstellar medium, and then you produce a diffraction pattern at the location of the Earth. And as the pulsar moves relative to the Earth and the interstellar medium, this diffraction pattern changes, and that causes actually slight variations in the observed pulse shapes. They may be very tiny and impossible to observe, but one way of detecting them is actually using what we call scintillometry, where you do take a look at this dynamic spectra, which is the frequency, the signal pulse intensity as a function of frequency and time. So this is the diffraction pattern on the sky as it moves across the Earth. And if you take the Fourier transform of that, you find this interesting parabolic arcs, which basically give you some information about the scattering screen and its location, and that's what it does with time. And if you observe this effect as a function of time, as we've done, for instance, with our telescope at Effelsberg, you see that it's varying with time. And so what you basically introduce is not only a variation in dispersion measure, but also variation in scattering. And that, if you take a Fourier transform of that, you actually get a kind of a signal of the same amplitude that we would expect from gravitational wave background. And if you have a screen that covers more than one pulsar, you may actually produce correlated noise of the right order of magnitude. So we really have to look at this very carefully and not being fooled by this to mimic gravitational wave signals. And I can talk more about this later on. So we really need to see the Hellings and Downs correlation curve. Eventually, if we get enough signal to noise, we can even pick up single sources, single supermassive binary black holes. That may not be possible with the current generation of radio telescopes, but with the SKA, we expect this to happen more than once at least. However, in order to confirm the signal, if it is real, we need certainly more sensitivity and better data. And there are two ways of getting this. One is bigger telescope, but also is more pulsars, because what you need is the different baselines between pairs of pulsars. So if you have n pulsars, you get n square pairs of baselines. And so square root of that. So the array basically scales linearly with the number of pulsars. It's not true. It's not true for all signal to noise regimes, but just as a rule of thumb, more pulsars can give you better sensitivity. Let me move on. So bigger telescopes is certainly the better way of improving the sensitivity. And there we have actually now, of course, the huge FAST telescope in China. We have the GMRT in India, which is now joining the pulsar timing array efforts. And we have the new Meerkat telescope in Southern Africa, which is the precursor to the SKA. We also have, and I want to mention this, LEAP. Actually, for already 10 years. For 10 years, every month, we combine the 5 biggest dishes in Europe to form a 194-meter dish, where we actually have a phase coherent addition of the signals, and really the signal to noise then adds linearly, and we can really produce sensitivity that corresponds to a 200-meter dish fully flexible on the sky. FAST is 500 meters across, but the effective collecting area is 300 meters at an instant of time. And Meerkat is 7 times more sensitive than the Parkes telescope. So that's really going to be a game changer once we add the Meerkat data into our system. I'll skip that. We actually provide S-band high frequency receivers for Meerkat from our institute, and that will improve the timing precision enormously. When are we there? This is a plot from Stephen Taylor and colleagues from 2016, where we tried to detect the expected detection probability as a function of time. The blue and red line makes different astrophysical assumptions along the lines I've tried to explain earlier. In the most optimistic case, we should basically, in the current sort of PTA, single PTA efforts, be on the verge of detecting something. There's an update to this. Renee Spiegberg is looking at Meerkat data, and this is a plot in her paper, which is basically an ideal IPTA 125 pulsar pulsar timing array. Here's the EPTA nanograph is in red. So we may just be about at the verge of detecting something. So maybe seeing the red noise signal is actually indeed the first hint, but let's see. I was mentioning the frequency range. So let me explain why we sit here in a nanohertz regime and how we can try to push the frequency limits. Basically, the frequency we're sensitive to is basically 1 over a year, because we need to observe the pulsar for at least 1 Earth orbit. And that naturally gives you the nanohertz frequency range. On the low frequency side, we're limited by red noise processes, also intrinsic to the pulsar. But on the high frequency side, we're basically limited by the cadence of our observations. So if you just take the cadence as such, then 1 over a month, which had been the typical cadence, gives you 400 nanohertz. And the low frequency, if you also take here the observing length as the lowest possible frequency, you get about nanohertz. That's why we are naturally in this regime. We have actually had an observation of 1 pulsar continuously for 24 hours. This is this global observation of 1713, where we handed one pulsar from one telescope to the next, and that pushes us here to the 10 to the -4, 10 to the -3 hertz frequency range. But we also had actually observation of 1 pulsar for more than a year with 1.6 day cadence within the European pulsar timing array, and that really gives us some very nice sensitivity up to 5 microhertz. We didn't see anything; it's only 1 pulsar, so we're limited by sensitivity, but it shows what it is possible if you can repeat this in a more regular fashion. And in fact, the new EPTA data set has an average cadence of about 1 to 2 days. For more than just 1 pulsar. If we get detection, that's probably all we can do with it, actually, at least with the current generation of telescopes. But with the SKA, as we already pointed out in the first SKA science case, we can do much more. And I'll just briefly discuss this. So with the SKA, we would mostly use what we call the SKA mid array, which is the sort of extended meerkat. With the SKA and the sensitivity that we then would have available, we can actually get single source detections. We can also then localize them on the sky to a precision that we can follow up at other parts of the electromagnetic spectrum. We can actually do then also gravitational wave astronomy and also do fundamental physics, as I'll also show you in a second. Before I do that, let me point out that with the SKA, and this is part of why it's so much better than what we have today, we can basically get a position of the pulsar on the sky, on the distance, a parallax, so that we can get this within 1 wave cycle of the gravitational wave. And that allows us to use not only sort of the impact of the gravitational waves on the space-time around the Earth, but also on the pulsar. We call this the Earth term and the pulsar term. Currently, we only use the Earth term. That's why the correlation coefficient is actually 0.5 rather than 1 in the Hellingston and Downs curve. But if we actually would also be able to locate the pulsar, we can then sort of use the 2 contributions, not as a noise source, but as a source of information. And the way we, let me skip this because just you have seen this in the past. But what happens actually that the pulsar term gives you a retarded access to retarded signal compared to the impact on the Earth term. So for instance, if you have a gravitational waves hitting the Earth and hitting the pulsar, it will basically give you the access to the history of the evolution of your binary system. So you would have a contribution of different frequencies to your single source signal. Basically, it's the composition then of 2 parts. If you have a sort of a 2-arm pulsar timing array, you have the gravitational wave impacting on the pulsar, and you have a gravitational wave impacting on the Earth. And because of the different source evolution at the time when the gravitational wave hits the Earth, you get different frequencies, and hence its frequency structure due to retardation. In fact, if you would—
Sorry to interrupt, you have 5 minutes.
Yep, that's fine. Thanks. So if you actually then have many pulsars locating the same source, you can really sort of trace the history of the source back in time, but just looking at the decomposition of your frequency signal in the final detection. We can also look at we can actually localize the signal much better, the SK much better, and just refer to this paper by Katie Lee et al., where we showed that we can localize the source depending on the signal to noise ratio that we have to about 1 arcmeter on the sky, basically doing triangulation of the gravitational wave source by using the pulsar terms and the Earth terms, and that allows us to do multi-messenger observations. Having good precision, we can actually also look for deviations of the Hellings's and Downs curve. For instance, if we have polarization modes, then the Hellings's and Downs curve will be different depending on which breathing modes you have, and also if the graviton has a mass, then basically the universe space-time acts as a waveguide. You have a cutoff frequency, and that will also modify the Hellings's and Downs curve depending on the graviton mass. So if you have enough precision, you can sample the Hellings's and Downs curve very precisely, then you can have access to the graviton mass as well. So that allows us to look at some alternative gravity. There's more which I won't be able to discuss, but we can also look at strings, dark matter, axions, and so on. And this is a nice work. If you want to learn more about this, look at this a review by Sarah, where she basically looked at a number of possible contributions to the signal that we would observe. Finally, second last slide, there's a lot of complementarity between PTAs and other detectors. There's not only the frequency range, there's also that if we have emerging supermassive black holes, we basically pick them up before the merger in a pulsar timing array, then LISA will certainly see the merger. And if there's a memory effect, we can also measure this with a pulsar timing array. And so there's a nice complementarity. And look at this paper here by Kaiser and Williams, which sort of tries to combine this also in a source reach, but there's no time to talk about that. Finally, summary conclusions. I think we are on a good way of making detections. I would caution that what we have seen so far is a detection. It may be, but it's not yet clear. We need to control our systematic effects, and we need independent data analysis and cross-checks between the different telescopes. The IPTA is certainly the way to go. I think a secure detection will require further sensitivity, but fortunately we have fast MECA, GMAT, and other facilities coming up online. But this is really just the beginning. I think with future facilities like SKA, like NGVLA, like FAST, we can do much more. So I hope 50 years after pulsars provided the first evidence for gravitational waves, we can actually use them also at the gravitational wave telescope. So thank you.
Thank you. Thanks very much. Let us see if there are any questions. For now, there's nothing on the chat. And I see no hands raised. Let's wait a few minutes. Yeah, there's a hand raised by David. Go ahead, David.
Thank you for the really nice talk. I maybe like a silly question, which is kind of about this second last slide you had on kind of the number of pulsars in the array against the precision. So we always hear that kind of as you collect more data with the current set of pulsars, that improves sensitivity. So could you comment kind of on how increasing the number of pulsars and also increasing the duration of the data set both influence the kind of quality of the data that you have and your ability to provide a detection? Like how do these two relate to each other?
Sure, there are different ways of doing it. First of all, in principle, you need to distinguish between whether you're in a high signal to noise regime, low signal to noise regime, and so on. There's a nice paper by Ravi Siemens and collaborators who sort of go through all the different cases. But the basic idea is, as I said, the more pulsars you have on the sky, the better you can sample the Hellings's and Downs curves. And that's really required to actually trace the curve. Only if you really follow the curve properly, you can be sure that you have a detection. And that just goes linearly with the number of pulsars, essentially. If you have a longer data set, you of course have a better frequency coverage. That is one thing, but also in principle, you can then also break up the longer wave time series in smaller, cross-check your data and so on. And with more pulsars on the sky, you can also do subarrays. You can drop pulsars from your analysis, see how sensitive your detection is for including certain pulsars and not. And all of that gives you much better handle on the quality of your data on the detection. So if for instance, if the detection would be just dominated by one source, it's likely to be not real. If it's so, you can also, of course, you want to get the full helix and downscape across the whole sky, not just the northern hemisphere or the southern hemisphere. So you really want to compare samples on different hemispheres, so that all of that gives you a better feeling about whether your sensitivity is correct or not. But the correct sensitivity calculation is essentially a square root of time for detection and number of pulses linear rule of thumb. There, but the exact numbers depend on the signal to noise regime that you're in.
Thank you for that really detailed answer. Really appreciate it.
No worries.
We have an additional question for Salvatore. Please go ahead.
Mm-hmm.
Hey, Michael, thank you for the talk. I have a somewhat sociological question coming from the LIGO-Virgo collaboration. Have you folks ever considered the possibility of a blind injection channel? Because at least for us, that was really when people thought seriously about how do we convince ourselves and the community that what we see is real.
Yes.
And you may be close to that point.
Yes. Actually, we have done this from the very start. We always had software that was able to put in the fake signal. In fact, some of the, we've also did data mock exercises, mock data exercises where we injected a signal and asked people to see if they can get it out of the data. But that was mostly for simulated data. But now, in fact, we are putting down a laundry list of things that we really want to check and verify. And one of these items will be clearly, again, this injection of a fake signal, and see if you can find it. And no, we definitely have, this is in our plan, yes.
Thanks.
Thanks very much. I see no other questions, so I thank all the speakers. I guess I speak in name of all of us. The talks were all very nice. And I think we can go to coffee break. I don't know. We are 5 minutes late, so maybe, I don't know at what time we reconvene. Maybe the organizers can define that. I guess we reconvene at the standard time, right? Okay.
Yes, if we have, let's try to get back